to be here. Really been looking forward to this, actually. It's nice to be able to talk to high school kids and yeah, just outline a few things about science, and particularly marine science, which is fantastic. So I was, my talk is really on the impacts of greenhouse effect, so really global warming, and how that is affecting our marine habitats and coastal communities. But first of all, I thought I'd just give you a little bit of a background into who I am and how I became a marine ecologist, or a marine scientist, I suppose. I was born in Tasmania, and we really had a lot of coastline around there, lots of bays, lots of beaches, beautiful promontories with rock pools and rocky areas. So I spent a large chunk of my youth, childhood and youth, actually fossicking around in the rock pools and around the beaches and so on. You can see on the left-hand side there a crab underneath a little crevasse, and some kelp, a crevasse as well. So those were typically the sort of areas that I'd really be playing around with, and spent a lot of time also fishing with my uncle up on the East Coast. So really spent a lot of time around the coast. So even when I entered high school, I didn't really know much about marine science or marine ecology, so it wasn't really on my radar. Going into what we had, matriculation college. So when I was your age, I was in something called matriculation college. And at that stage, when I was about your stage, I was really looking at becoming a geologist. So I've moved well away from that and gone into marine science. But I really feel that growing up in that sort of environment where a lot of the natural environment was around me, particularly the coast, really led me from being that as I don't know how old I'm, only a year or so old there, probably even a bit less, going to that on the right-hand side, which is me when I submitted my PhD. And that's when I really became what I say is a trained marine scientist. So we did quirky things like that when we were going through university. I came over to Western Australia when I was started my undergraduate. So I did my Bachelor of Science in Biology at Murdoch University, and really started to get keen in marine science, doing some of the units during that degree. So that's really what sparked my my interest, I suppose, in becoming a marine scientist. Then, of course, I did my PhD. And on the right-hand side, you can see I did my PhD on whiting, and part of that was actually collecting fish frames from fishermen to study the biology of King George whiting. So the only unfortunate part about that was that I didn't actually get to eat the flesh off them because they were already taken. Then after my PhD, I became a postdoctoral fellow, moved up to Edith Cowan University and got an academic position up there. And really the rest is history now. I've now become a professor, and we developed a centre at ECU called the Centre for Marine Ecosystems Research. So we do a lot of research in applied research and fundamental research in marine ecosystems, and how the various marine ecosystems actually are interconnected and operate. So my talk is really structured around, firstly, looking at the human drivers, the man-made drivers, particularly greenhouse gases and global change in general. Then I'm going to talk about ocean warming and marine heat waves and a little bit more. Then I'll go on to discuss disturbance ecology, because disturbance ecology it's really fundamental to understand that before we actually understand how ecosystems change as a result of climate change or any other man-made disturbance. And then I'm going to be talking about iconic habitats. I'm going to focus my talk on seagrasses and kelp, mainly because I reckon they're really awesome habitats or ecosystems, and they really provide a really important part of our ecosystem in general, our marine environment. Then I'm going to talk about the impacts on those habitats, and then talk about a process called tropicalization. I'll come back and I'll describe that a little bit later, but that's to do with global warming. And then talk about the broader seascape impacts. So those impacts where you have an impact on one habitat and how that then might have an impact on some other ecosystems. So when we're talking about man-made or human-made drivers of ecosystem change, certainly the topical point at the moment is global change through ocean warming, heat waves, storm events, and we've seen some of that over the last few days, and ocean acidification. But other impacts that are really sitting alongside those broader impacts are through pollution, so nutrients as an example, eutrophication, light reduction, which can also be related to pollution, and species invasion, of course, over harvesting of fisheries, which you can see down below, a typical trawl fishery. Go and talk about greenhouse gases. You've all seen these sort of graphs before, I'm sure. We're seeing an increase in the emissions of carbon dioxide because we're pulling out a whole bunch of fossil fuels from the ground, and we're burning it and releasing CO2 into the atmosphere. So really over the last 150 years, there's been an increase in CO2 emissions, and particularly over the last 50 or so years, there's been a really rapid increase in those in carbon emissions, carbon dioxide emissions. And of course, as a consequence of that, most of us believe, there are some deniers, but most of us believe that the atmospheric CO2 is increasing as a result of those carbon dioxide emissions. And that purple line there indicates the increase. And I don't know whether you can actually see my cursor, but there's an increase in the carbon dioxide, the concentration of carbon dioxide in the atmosphere. Now that then increases the amount of greenhouse gases that are in the atmosphere. So if we look at the left-hand side there, we can see that that's sort of a normal situation where the greenhouse gases are actually what saves our planet from being too cold, so we can actually inhabit the Earth, and we have a huge biodiversity associated with that. But of course, with an increase in carbon dioxide and methane as another major greenhouse gas, then of course that increases the amount of heat radiation that comes back into the atmosphere or stays in the atmosphere. So we'll gradually see a warming of the planet associated with those greenhouse gases. I'm not going to dwell too much on that. I really want to focus on those increases in temperatures that we're seeing, first in land, and then we'll come to the ocean. So here we can see an increase in the temperature. Now what we have here is on the y-axis, it's the temperature anomaly. So that is based on the average of the temperatures that we saw during 1951 going through to 1980. So anything above that level indicates there's an increase in temperature, and of course below that level there's a decrease or a reduction in temperature. So we could see that prior to the 1960s or so, then temperatures were pretty much below or at about that average level. But since the 1970s, there's been a real increase in the land temperatures. And if we look overall, and this is just not the land temperatures, but this is sea temperatures too, then this graphic video actually shows really nicely just how the temperatures have increased over the last 150 or so years. You can see here, oh, there we go. So just watch out for the amount of orange and red that really starts to show, certainly around about the 1950s, 60s and 70s. So you can see there that there's always oscillations in temperature from month to month, season to season, and year to year, depending on the climatic conditions. But you can see the overall trend that there's more orange and red appearing. Now we're going particularly to the 1980s, 70s and 80s, and now towards the 2000s, you can see there that there's a lot more red and a lot more orange, indicating that the temperatures, both air temperature and ocean temperatures, have increased over time. So we see on the top graph there, we've got the ocean, the sea temperatures, and there's been a 0.8 degrees Celsius increase in 35 years. It's around about, it was about 0.1 and then 0.2 degrees per year or per decade, sorry, that was being increased. So this top graph shows the global ocean temperatures. You can see there from the 60s to 70s upwards, there's really been an increase in the global ocean temperatures. More broadly also in the Indian Ocean. And in the red, you'll see there's actually an increase in the WA waters, and that increase has actually gone above the global and the Indian Ocean temperatures close to the coast. So that's indicating that there are some clear global temperature increases in the ocean. Of course, along with that, we see an increase in storminess, and certainly the last few days shows you a good indication of that level of storm. That photo on the right-hand side in the centre there shows some of the damage that was done down at Port Beach near the cafe and the Surf Lifesaving Club just on Sunday night and Monday. So that was an exceptional storm, and we're seeing more of those storms occurring as the years go by. And of course, we're also seeing increases in the sea level, and you can see there the graph down here. There's a gradual increase in the sea level, around about 1.5 millimetres per 100 years, but that's increased to about 5 millimetres over the last 10 years. So we're really seeing an increase as that the ocean is warming. Of course, it's expanding. And of course, we're seeing the ice caps melt as well, increasing the amount of water that's in the ocean. And that figure, that photo on the bottom right there, shows the blue boat shed in around Crawley, and the height of the estuary level at that particular time over the last couple of days. So really, really high sea level increases. What we're also seeing as a consequence of the global warming are heat waves. So we're calling them heat wave events. That's where the temperature of the ocean increases well above average temperatures, and that remains at those temperatures for some period of time. We can see that's occurred in 2003. There's been a heat wave in the Mediterranean Sea over to the left-hand side there. And in 2013, 2015, there was what was called the blob. Sounds like something out of a horror movie. Occurred off the coast of the west coast of the US and Canada in 2013 and 2015. And then there's also been an increase in 2012 in the northeastern side of the US and Canada. Now, if we go down to Australia, then we saw a heat wave in 2010-2011 summer. So this was a major heat wave where temperatures actually increased by up to about 5 degrees above average, and had major consequences on the east coast, on the west coast rather. And I'll come back and I'll talk about those because they're really the case examples that I want to describe. So this figure here shows the increase in the temperature associated with that heat wave event. Now, if we think about Western Australia, I don't know whether you're aware of the Lewin current that comes down the west coast, but that's a warm current that comes in through the Indonesian archipelago, or it starts to form after the water effectively is flowing downhill from the Indonesian archipelago, and then that flows around to the west coast of Western Australia. So that varies from year to year, depending on the strength of the El Nino and La Nina phenomenon. And that in strong Lewin current years can increase in the temperature across the whole of West Coast. In 2011, around about February, then that really increased. There was a significant increase, a huge increase in temperature going up to about 5 degrees. And that was, that really affected a large part of the coast going from Shark Bay, even going down to Jurien Bay, Kalbarri and Jurien Bay. And I'm going to come back and talk about some examples of the impact of that particular heat wave event as examples of how global change is occurring. But before I do that, I really wanted to give some basics about disturbance ecology. It's a fundamental process where we need to understand how that works in order to understand how we're actually impacting the marine environment and the terrestrial environment, come to that. So if we think about this graph on the left-hand side here, think about the oscillations here, which is the environmental change, which is occurring on an annual basis, seasonal basis. And you have the health of the seagrass that oscillates up and down, depending on those environmental changes. And that's pretty much a natural event anyway. You have differences between years, you have differences between seasons. And so the resilience of the system will be based around much of those normal annual changes and seasonal changes. So the system will remain sort of pivoting backwards and forwards in much the same way that if you're on a roller skate in a roller skate park, then you'd be going up and down and end up with an average right down in the center of that curve. Now, as the environment changes more and more, and you've got more environmental stress placed on the system, as shown here between the 1900s and 1970s, there's a far greater environmental stress, particularly associated with temperature. That will mean that the health of the seagrass will flip up onto this flat area here and then eventually flip down into a new paradigm, I guess, in where the whole system has altered from something that's dominated by seagrass, in this case, or it could be kelp, to something that's dominated by algae. And you can see here on the right-hand side, the figures show healthy seagrass on the top, and then that shift in the seagrass down on the bottom where it becomes much more dominated by algae. So that's disturbance ecology. And if we look at it in a different way, then we're looking now at an example using kelp forest. Then a kelp forest, as I said before, will go through these oscillations in terms of seasonal changes and annual changes with general patterns in annual disturbances. And providing those light levels and the physical abrasion and so on don't get impacted too much, then you'll have recruitment that occurs and then that kelp forest will remain very, very healthy. If, however, you have something like global warming or heat waves or particularly strong storm events or acidification, a whole range of other human disturbances, then you can actually see a change in the system. And so what's happened here, or what's represented here, is that the kelp has gone to a much more algal or turf-dominated reef. And so now the recruitment of the kelp is too low, or if the recruitment is still high, you might have herbivores that graze down on those new recruits and keep that reef as a turf algal reef rather than the kelp-dominated reef. So that's where you have this fundamental shift in the ecosystem. So the health of the system has changed, has been impacted, and the actual dynamics of the system have changed completely. So what I'm going to do now is talk about the marine habitats just briefly. I'm going to talk about seagrass and kelp predominantly. I'm not going to talk about corals, although they are another iconic marine habitat. But the media, because of the clear indications or the clear impacts that are shown in those systems, then the media has really given a lot of attention to those. But those poor seagrass and kelp cousins don't get the same amount of media attention. They're both highly productive systems. They're really old systems. They both photosynthesize. They provide really, really important habitats. So seagrasses and kelps do awesome things. Seagrasses, particularly kelp, they protect our coastlines. They clean our water by taking up nutrients and pathogens. They feed a whole range of animals like the dugongs and the parrotfish below, particularly in the tropical environments. And they provide a home for a whole range of different marine creatures. They capture carbon and they also export material to other ecosystems shown here on beaches. Kelp do pretty much the same thing. They're iconic habitats for a whole range of things, and one of my favourite fish are the leafy sea dragons. That'd have to be my favourite fish. I think they're really, really, really cool. And one of my favourite mammals, of course, is the sea otter. They're really cool as well. And they really do rely very much on the urchins that live in the kelp forest, particularly along the west coast of North America and South America. But there've been large impacts associated with those habitats. So seagrasses losing something like 1% per year up to 1940, and then that's increased to 7% per year since 1990. So large impacts. We're seeing major losses, as you can see here, in terms of the red on this graph indicate the amount of loss in different regions around the world, particularly North America and Australia and Europe, where most of the studies have been done. And you can see on the right-hand side that increase in the area of seagrass that have been lost, since the 1970s, 80s and 90s. That heatwave event that I talked about, the 2011 heatwave event, had a huge impact on Shark Bay. Major seagrass loss. So if you look at the seagrass area in 2002 in this map on the very left-hand side, large areas of seagrass, where if you go to 2014, after that 2011 event, then the amount of seagrass was much, much lower. And this bottom figure shows in red, the amount of seagrass that was lost. So massive amounts of loss. And you can see that on the right-hand side in that graphic there. And visually, you can see it in the bottom right-hand photo here. So large losses of seagrass. That, of course, has some flow-on effects to the fauna that actually survive and depend on seagrass. So you've got the green turtle as an example, dugongs, so 60% reduction or impact on dugongs, on green turtles that feed on seagrass, and of course the other organisms like sea snakes that cruise through seagrass are also impacted. And the scallop fishery was also closed, although that's not necessarily just related to seagrass loss. If we look at impacts on kelp forest, then we're seeing a similar sort of pattern, really. We're seeing big losses of kelp. So again, shown in red here, they're being lost at around about 2% per year. In some regions, even much, much higher. So North America, Europe, and again, Australia, where most of the research has been done, we're seeing some big losses. And this shows on this graphic below the amount of loss that's occurred. So if we look at the impact of that heat wave on the kelp forest, you can see here on the very left-hand side, the blue and the red little bars indicate the change in sea surface temperatures. You can see here in 2011 a large increase in the amount of in the temperature, and that has sort of continued to occur since that period as well. So there've been much more warmer events occurring since that 2011 period compared to prior. You can see that all the temperature levels are below that zero anomaly. You can see here that on the graph here, the line graph, that there's been a major drop in the amount in the percentage cover of kelp on the reefs. But at the same time, there's been an increase, a massive increase in the percentage cover of seaweed turf or turf algae. So that indicates that you have really this ecosystem shift from a kelp-dominated system to a turf algae system. You can see the effect of that loss. So here on this middle graph, we can see the red indicates the amount of kelp that has been lost as we go down the coast. So large, almost complete loss in Kalbarri, going right down to significant losses even down to Jurien Bay. And as we go further south, then around Perth, then there've been losses, but not as much. And that's because the temperature effects weren't as much. What we can see on this graph is an indication of the species assemblages, so the similarities in the species assemblages. If we look at the blue here, that circle of blue, then that indicates the species assemblage of seaweeds in Perth, and the red indicates the species assemblages in the tropics, it's up around Ingaloo. So they're areas that, so here you have a tropical dominated system up here and a temperate dominated system here. In Kalbarri, prior to the heatwave event, then those seaweed assemblages were much, much more similar to Perth. But after that heatwave event, then they're much more similar to the tropics. So we're seeing a real shift in the assemblages, moving to a tropical assemblage after that heatwave event. And the same occurs, and I can't quite see it because of these, I'll just move that. Same again for the fish assemblage. So you're moving from a temperate fish assemblage to a more tropical fish assemblage after that marine heatwave event. Now, so that's what heatwave events, that's sort of impact that the heatwave events have had. And that's really from what we sort of call pulse events. Because what we're seeing is a broader change in the temperature, an increase in the temperature in the ocean temperatures, and that's leading to some gradual changes in the fish assemblages and the algal assemblages. So what we're seeing in that process, as the ocean warms up, we're seeing a movement, a change in the distribution of those tropical species in those lower latitude areas, so closer to the tropics, moving down towards the temperate regions like Perth. And that's occurring in a range of different locations around the world. This process is called tropicalization, and we're seeing that it's occurred in the Mediterranean, where the Suez Canal has allowed a whole bunch of tropical species to move into the Mediterranean Sea. We're seeing it in Japan, and we're also seeing it on both the east coast and the west coast of Australia. So if we look at Japan as an example, the reefs around parts of Japan were dominated by a kelp called Ecology cava in the early 1990s. There was, with gradual increases in temperature, then we see a change in the amount of Ecology, that's the kelp, in 1994, to the point where by 2000, then that kelp has actually been completely removed and it's being replaced by turf algae. And that's partly facilitated by the herbivorous fish species, such as rabbitfish and parrotfish, that have been moving up into those areas at the same time. And then by 2013, and this is really a fundamental shift in the ecosystem structure, those same areas that were dominated by kelp in the 1990s are now dominated by corals in 2013. So that's occurred over a 25-year period. So pretty amazing change. Of course, we're not going to be exempt from those changes. It certainly has shown a dramatic change in Japan, and we've seen similar changes up around Kalbarri too. So some of the reefs around Kalbarri are now dominated by coral reefs rather than kelp. And we're going to gradually see that occurring down here in Perth. So what I'm going to talk about here is some of the work that I've been working on recently and predicting what's going to happen in Western Australia. So if we look at seagrass, then this graph here shows the blue indicates what the distribution of the different seagrass species are around about now versus what they're going to be in 100 years or less than 100 years time at the turn of the century. And we've got a scale here of 400 kilometres. So we're seeing here the Cymodosia species, tropical species. It's really going to be moving from north of Exmouth going down to Shark Bay by the end of the century. And we're seeing here that some of the more temperate species are going to be shifted, like Thrasodendron is going to be shifted from north of Perth, so around about the Geraldton region, and it's going to be shifting right down to the very southwest tip of Western Australia. And beyond that, it's really got nowhere to go. So it's really going to fall off, if you like, off the seascape. Fauna, we're going to be seeing similar things. We're going to be seeing a shift in some of the tropical species, like the parrotfish and the rabbitfish moving down. So they're moving something like 300 to 400 kilometres and moving down into Perth by the turn of the century. And some rabbitfish, like this one here, have actually already made their way down to Perth. Some of the temperate species are going to be shifted much, much further south towards the southwest tip. Now, I'm not sure how we're going for time, John.
We've got about 10 to 15 minutes left, all up.
Of my talk, or with questions as well?
All up, yeah. So with questions.
Yeah, okay.
As well.
So I'll take another about five minutes and then go on to talks. So what we're seeing, or what we're predicting, is, so this is a tropical system here where it's dominated by dugongs, tropical seagrasses, dugongs, green turtles, and grazing herbivorous fish. And this is a temperate species where we don't really have many of the grazing species of fish and mammals and reptiles at all. The first wave of that change is going to be when those herbivorous species move down into the temperate species, which are still going to be dominated by temperate seagrasses. And they'll start to feed on the seagrasses, and that's going to change the whole dynamics of the seagrass systems. But ultimately, there's going to be a shift in the tropical species of seagrass. And so first, there'll be a loss of the seagrasses, the temperate seagrasses, and then there'll be a change in the dynamics, and there'll be a change towards the tropical species of seagrasses. And then will ultimately become a much more tropically dominated system. So that's certainly not going to occur over the next 80 or so years, but certainly 150 or 200 years. And another area of work that I'm working on, and this really relates to those seagrass and kelp losses, is what's happening on sandy beaches. So this is what's going to happen over a broader seascape scale, where we see a loss of seagrass and kelp, which would normally make their way onto the beaches. And this is some work that I've been doing with some international colleagues, where we've been showing just how much kelp and seagrass actually accumulate on the beaches around the globe. The important point is that kelp and seagrass are really the dominant feature of the rack, what we call rack on the beaches, right around the globe. In the surf zone and on the beaches, they really do form important habitats for a range of different organisms, like amphipods, where you can see an increase in the amount of rack, which is mainly seagrass and kelp, really increases the density of those amphipods, and they become really important food for fish. Like here we've got the trumpeter whiting and the cobbler, juveniles of those, and we see an increase in the abundance of those species, and also the diversity of fish species in the surf zone associated with rack. And so if we see a loss of the material that's coming in, so here we have a schematic diagram of the kelp and seagrass that comes in and settles into the surf zone and onto the beaches. If we lose that, then we lose all of the trophic aspects and the habitat benefits of those different types of rack material. And we'll see a whole change in the ecosystem structure. So in summary, carbon emissions lead to global warming and heat waves, and cause ocean acidification and more storms and so on. The heat waves will lead to loss of habitat in seagrass and kelp, and that's going to occur has been occurring over a matter of even months in some locations. That can lead to a loss of ecosystem function, and can lead to broader impacts at the seascape level, such as in sandy beaches. Ocean warming will also lead to tropicalization, so a shift in the actual distributions of species, whether it be seagrass or fish or corals, down into the temperate region. So tropical species will become a much more part of the normal part of temperate systems, what we see now as temperate systems. So that's going to lead to a major ecosystem shift. We're going to see those, what we see now pretty much as temperate systems, being shifted much further south. So with that, I'll leave it there. And thank you very much, guys, for listening. So any questions? And I'll come out of this, I think. Right. I'm opened up to questions.
Okay.
Sorry, Glenn,
do you think
one of my questions.
Right, that's Sacred Heart, I think I can hear now.
Oh, that's too easy. Okay. Do you think that the heat waves are occurring due to long-term climate change or due to decadal changes like El Nino or Indian Ocean dipole impacts?
Good question. Very good question. It's a combination of both, actually. So what we're seeing is we are seeing decadal patterns in El Nino, in the Enso cycle, and that leads to an increase in the water temperature, particularly in the La Nina years. That's an increase in the water temperature above on the northern part of Australia, which actually then leads to the formation of a stronger Lewin current. So that's a normal cycle, and the Lewin current and strength of the Lewin current and the warmth of the Lewin current alters as a result of that. But what we're seeing is on top of that, there's an increase in the ocean temperature more broadly. So that means that there are going to be more heat waves on top of an already increased ocean temperature as well. So that will lead to not just more marine heat waves, but a change in the form of the habitats that occur. Did that answer your question? So I think somebody's waiting.
Okay. Why are WA waters warming faster than the global average?
That's that's a good question, and I think I'm really not the best person to talk to. Charu or Ming Feng is probably going to be a better one later on. I think Ming's giving a talk a little bit later on. But one of the reasons is that we do have the Lewin current. So we're unusual for a west coast of any continent in that we have a warm current that comes down from the equator towards the pole. That brings warm water down the coast. If you look at Africa and South America, then they have currents that actually go in the opposite direction. So they have cold currents going up their coasts. We have a warm current that's coming down. So what's happening is that Lewin current can get warmer and is actually increasing our temperatures. There are other factors that I'm sure Ming Feng would be able to come back and talk to that overlay that, but that's one of the reasons.
Hello.
Hello.
Is a loss in seagrasses and kelp beds going to have a negative impact on fisheries, or will there be positive impacts like increasing rock lobster?
Yeah, well, neither will have a negative impact. The interesting thing, you bring western rock lobster up as an example. That's a species where the juveniles recruit into the reefs, and then they forage on both the reefs and in the seagrass meadows. So they're dependent on both the seagrass meadows and the reefs. So if you have a loss of kelp, then you have a loss of a real change in the understory. That's a type of algae that's underneath the kelp, which is what they feed on. Plus also you'll have an effect on the seagrass and the epiphytes. So they're the algae that grow on the seagrass, on which they also feed. And kelp and lobsters also feed on the invertebrates that live on the seagrass as well, that feed on the epiphytes. So they have a very broad diet, but they will be impacted. That species will very much be impacted by the loss of seagrass and kelp, and a whole range of other species will be impacted as well. Yeah. There's a question there. Somebody had his hand up.
Yeah. I think that's it from us, Glenn.
Yeah.
I think there's another question from Rockingham there.
Oh yeah, okay, fantastic.
Just got one last one.
What is the natural recovery time for seagrass meadows? following.
Sorry, you just faded out. I can't hear.
What is the natural recovery time for seagrass meadows following an extreme heat event?
Phew. They don't. The short answer to that depends on the species. So the species that we're seeing, species that have been lost up in Shark Bay, are what are called they're Posidonia species and amphibolus species, and they don't recover very quickly at all. There've been a whole range of different regeneration exercises down in Coburn Sound as an example. So where they've transplanted seagrass and put them into the sediment in bare sand sediments, and tried to look at the recovery of those. And the success is actually pretty minimal. There are some examples of success, but very, very few. So we're really looking at a loss of those seagrasses for either decades and decades, or not recovering at all.